So yeah, I kinda made my own voice chat. Welcome to another journey through networks programming, the difference between UDP and TCP, and a lot of other stuff. I hope you enjoy it. So the first thing I decided on was a programming language, and I of course needed something that works with my Flutter app. And luckily there was just a thing, called Flutter Rust Bridge. And as you might have already guessed, this is a package to link your Flutter and Rust project into one. So I could basically communicate between Flutter and Rust. And this is just an amazing project, and to whoever made this, you're an absolute legend. Now, since we want to be communicating over the network, we'll also need a server. So all I did is write a basic server in Golang that basically just takes all the traffic we send to it and redirects it to all the clients. So basically it's just an echo, and if you're sending something to it, everyone's getting it, except for you, yourself. This is of course also a little bit complicated the way I implemented this, but this is not what this video is focused on. Well, then let's get started with the hard part. Getting data from the microphone is already the first challenge. And for this, I used the CPAL library, because it is basically the best package to use in my case. But this is already where the problems start, because different microphones have different sample rates. For example, this microphone that I'm using right here collects 48,000 samples per second. And some other microphones, like my webcam up there, that I'm not using right now because I'm using my phone, collect 16,000 samples per second, which is like 3 times less. And you somehow gotta make up for that. Luckily for us though, the library I use to play audio, called Rodeo, can play audio at different sample rates, no matter what headphones or speakers you might have. So for me this means all I need to tell Rodeo is what sample rate the audio I want to play has. So all we just do is we append the sample rate of the voice data that we just recorded to the piece of data that we're sending to the server. So now every packet, which is just a chunk of data we're sending to the server, has this little sample rate indicator, which means we can now play it on the client without having to worry about the sample rate, and without having a constant for it. But sending 48,000 samples to the server is just a little much. So what we're gonna do for now is we're gonna apply something called a codec, which can basically reduce the size of the data we have to send. In my voice app, I use Opus, which is a commonly accepted codec that is basically used by everyone. Even Discord uses it, which is kind of why their voice chat is so good. To use Opus, all we have to do is have a basic encoder, which is basically like the machine that kind of transforms the voice data we have into something we can then send to the server, and then when we receive it, we just do the reverse. The reverse of that would be called a decoder. And these two magic machines just normally work, so we don't really have to worry about those, and if you want to know how those work, then you should probably watch another video, because I'm not going into much technical depth today. So our voice chat now consumes a lot less data, which is already great, but there are more improvements to make. Alright, but we didn't even talk about how we are sending it to the server yet. And there are 2 common choices we can make here. The first one would be UDP, with the second one being TCP. And those 2 protocols do something very different. Those 2 are kind of like the thing that is used to transmit the data you're sending to the server and to make sure that it's like arrived properly. Although TCP focuses much more on reliability, with keeping things like packet order and making sure every packet is received. But when every packet is received, that also adds a crap ton more delay. And that delay is a huge issue in our case, because we're literally making a voice application, and who likes talking with a lot of delay? And on top of that, the delay is pretty inconsistent, so that also makes things a little bit worse for TCP here. Which is why we're choosing UDP. But that also adds a lot of complexity to the equation, because now we have to somehow guarantee packet order and make sure that everything is working properly. And this is what the second part of the video is gonna be about. So even though networking sounds kinda complicated, it's actually not that complicated if you think about it as a concept. Implementation details are another different story. Alright, so let's talk about packet order first, because this is one of the biggest issues when handling voice chat. So in voice chat, this is incredibly important, because you don't want to have the next 20 milliseconds of voice play before the current 20 milliseconds of voice. And this can sometimes happen just due to network conditions, or just because your phone is trying to figure out its 4G or 5G connection. Alright, so the way we fix this is pretty simple. We're just going to have a counter on the client that is incremented by 1 every time we send a packet. And now all we do is we also append this information to the packet itself, so that every packet now has a sequence number. And then on the other end, which would be the receiver, we just use this number to check if the packet order is correct. And if it is, we're playing the packet. But this isn't nearly enough to prevent everything that can happen in a network. You know, there's also a little something that's called network jitter. And this is kind of a really hard problem to fix. So, what this means is basically, if you've ever played a game like Minecraft, you would know that your ping can vary over time. So for example, you could have 100 milliseconds of ping in the 1 second, and then just 5 seconds later, you're suddenly down to 30 milliseconds. And this creates a lot of problems. So what I do for my app is, we're just going to queue a few packets here. So to prevent this little difference, all we do is add a little bit of extra latency by implementing a queue. I know that this makes conversation slightly worse, but therefore your friend actually hears you, and by hear you I mean properly. So in my case, every packet contains 20 milliseconds of voice data. So my queue in this case has space for 4 packets, which means we add 80 milliseconds of extra latency. And this is of course not ideal, but it works for me. And we might even reduce this number in the future. Maybe we'll even change it based on network conditions. Anyway, one final thing I want to talk about today is if you out there, yeah, you the guy watching this video, should make your own voice chat if you have to implement something like this. And my answer is unfortunately no. Because there are so many better solutions that you could have used. I mean, just look at LifeKit. They have a completely open source version that gives you video calls, screen sharing, and audio. But the only thing they don't have is microphone sensitivity, which is why I made my own voice chat. And I know it's kind of stupid, but that's what I did, and you're probably gonna find a different solution for your problem. But, you know, if you want a little challenge, it's always interesting to make this yourself. And I implemented this without any prior Rust knowledge, so I didn't know what the fuck I was doing, but I still kinda managed to do it in the end. Although I still have a ton to do, you know?